Das ist, glaube ich, die Datenschutzrichtlinie. Okay, dann ist es mir eine Freude, den Vortrag von Stefan Perko vor. Wir können auf Englisch reden, glaube ich.
English, yes.
Yeah. Okay, it's a pleasure for me to introduce Stefan Perko. He's from Jena and will present a joint work with Stefan Ankirchner on the approximation of stochastic gradient descent. So, please.
Thank you for the introduction and for letting us, or me, present our work here. Again, this is a joint work with Stefan Ankirchner, and let's get right into it. So, this might be a typical situation that you have if you look at a cloud of data. So we're given some data points and we want to do some regression to predict the y value from the x value. And there are different regression methods that we could use here, but for simplicity, we will just consider linear regression in this talk. So this might be the result of a linear regression. And the question is, how can we determine this line? Classically, we can, of course, solve a system of linear equations, but now we want to consider something else. We want to consider using gradient descent. So if we perform linear regression with gradient descent, then we are considering a quadratic loss function over the capital N data points, xk, yk. And here we already centered the data, so we don't have to fit the intercept. We only have to fit the slope parameter to keep things simple. And this parameter here is p, which is one-dimensional. So what we do is we define gradient descent by saying, okay, xi n plus 1 is given by xi n minus a learning rate h times the gradient of f applied to xi n, gradient descent again. And in this case, of course, it's just a derivative because we're in dimension 1. And if we compute this, we can see, okay, what we're actually doing here is we're taking the average over all data points. And the step we're actually doing is we say, okay, xi n plus 1 is given by xi n minus the learning rate h times xi n times the sample variance of the x values minus the sample covariance of x and y. Again, the data is already centered. That's why that's actually sample variance and sample covariance. Okay. And if we perform this, we get a curve like this. In this case, the gray line is the so-called ordinary least squares estimator. And we can sort of see that gradient descent will converge to that over time. But looking at this curve, it just looks like an exponential function, right? So something else we can do is let's consider a differential equation called gradient flow, which in this case is given by dx0t equals minus nabla f of x ot dt. In this case, it's just a linear equation, depending on the sample variance of x and the covariance of x and y. And we can, of course, solve this explicitly, and we get this exponential function here, where we consider the difference between the initial value x0 and theta hat, which is the ordinary least squares estimator, times this exponential, so it's an exponentially decaying function, and the rate is determined by the sample variance of the x values, and then plus theta. So we see as t goes to infinity, this first summand just vanishes. The initial value doesn't actually matter anymore, and we just converge to theta hat. So, and to compare this solution to the gradient descent, we can say, okay, let's say that this continuous time point t is equal to the discrete time point n times the learning rate h. And if we do that, we can plot both of these processes, so the gradient descent in blue and the gradient flow in orange, in one coordinate system, and we see they are very close to each other. So in that sense, we can consider gradient flow to be a continuous time version of gradient descent. Something else we can do to compare these two is, let's think about simulating an ODE on the computer. Well, we can use different discretization methods. And one method we can use is the Euler method. It's not very good, but for our purposes, it will suffice and we'll get the right idea across. If we write down the Euler method, it's given by xn plus 1 equals xn plus a discretization parameter h times the coefficient of our ODE applied to the previous time step. And if we run this, then this Euler approximation will be close to x at n times h. But if we look at this, in this case, the Euler method is exactly the same as the gradient descent. We do it the exact same iterations as long as we say the learning rate h is the same thing as our discretization parameter. Okay. And that kind of gives us an idea how we can start with our gradient descent process, but then pass to continuous time. And initially, this seems like we make things more complicated, but I think in the end, the opposite is kind of true, because now we can use all sorts of analytical methods to study the behavior of gradient descent. It's often easier to do this in continuous than in discrete time. We can study whether gradient descent converges and how fast it converges, for example, or we could consider if we vary the learning rate over time, how do we have to choose it so that the loss at some future time point is minimized, which would be optimal learning rate control. Okay. But if you ever trained a machine learning model, for example, a deep neural network, then you probably have not used gradient descent, you used stochastic gradient descent. The difference here is we have a sequence gamma 0, gamma 1, and so on of independent and uniformly distributed random variables on the set of integers from 1 to capital N. And the effect this has is that at every time step, we choose from our data set one data point randomly, IID. And then we compute the loss with respect to the single data point, right? And then this gives us a stochastic algorithm where we only consider a single randomly chosen data point at each step. And this is a typical instance or realization of stochastic gradient descent. It doesn't have this sort of nice exponential structure anymore, although it will have that in the mean. But you can see we can still in the same time get pretty close to the old S estimator, even though the advantage here is that we don't have to upfront compute the average over all data points. We can just use a single one, so the individual steps are much more efficient, which is why it's often preferred in practice over batch gradient descent, or what I called gradient descent before. To make the comparison more direct, we can consider what kind of update step do we do on average. So we take the conditional expectation condition on the previous parameter estimate Gn, and we just treat the Gn as fixed, and then take the average over the x squared and x times y. And we see what we get here on average is the same kind of update that we had with gradient descent. So with this, we can decompose the stochastic gradient descent, or SGD step, into this first part, which is basically what does it do on average? And then we have to correct by this h times mn term, where mn measures the difference between the sampled gradient, or the gradient due to a single sample point, and the average gradient. So this mn part will have conditional expectation, which is just 0, but it will have a variance. Okay, and the bottom line here is that we can approximate gradient descent in continuous time with gradient flow. And then in discrete time, we have stochastic gradient descent. But what would be a good process to approximate it in continuous time? Because I would say it's more reasonable to also have a stochastic process continuous time to capture the behavior that SGD has. To introduce something like this, we have to talk a little bit about random walks and Brownian motion. Okay. So now consider, let's forget about gradient descent for now, and just consider a sequence of coin flips. So these are called Z0, Z1, and so on. And if the coin lands on heads, we record a +1, and it lands on tails, we record a -1. And then these variables have expectation 0 and variance 1. Actually, it doesn't matter that there are coin flips. We could do any IID sequence with this expectation and this variance, but of course, it's very intuitive with coin flips. And then we build a new process, Sn, such that Sn plus 1 is equal to Sn plus Zn. So what we do is we flip a coin. If it lands on heads, we go +1. If it lands on tails, we go -1. We repeat this a bunch of times. And then we can get a curve like this. So in this case, we had tails, 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 heads, tails, heads, tails, tails, and so on. I think it should be clear how this curve came about. And it should be noted that, of course, if we rerun this process, we would get a different realization. The same thing stochastic gradient descent. What we can now do is we introduce a small parameter epsilon and define W epsilon basically as our random walk, but at time t over epsilon. So if we make epsilon smaller, then t over epsilon becomes larger, which means we go through our random walk faster. If we make epsilon smaller and smaller, then the variance of s would then of s of t over epsilon would go to infinity. To compensate, we have to multiply with square root of epsilon so that actually it stays the same as we decrease our epsilon. And we can look at the effect of this over here. So we have a random walk with this sort of epsilon scaling for different values of epsilon, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and 10 to the minus 4. And as you can see, as epsilon becomes smaller, the sort of random walk becomes closer to something which looks like a continuous process. Of course, the single path always looks a little bit different, but overall we see sort of that the paths together seem to converge to something. What does it converge to? Well, if we recall the standard limit theorem that basically explains why the bell curve occurs so much in data that we sample, it tells us that as we let epsilon go to 0, then at this W epsilon at t converges to something Gaussian, where specifically it has this WT has mean 0 and variance t. But this would be for a single time point. But we can also like describe the structure between different time points, for example, the covariance. Donska's theorem extends this convergence to the entire function, and this W epsilon converges to something called Brownian motion as epsilon goes to 0. Without giving you a definition of Brownian motion, if you just think about this bottom right picture, this is kind of how it looks like, or this is a single realization, more or less, of Brownian motion. And it should be noted that this convergence holds just if we know that the expectation of zk is 0 and the variance is 1. So this holds for many different distributions. We will, in many cases, will get Brownian motion in the end. So we can extend our table here a little bit. I added that the Euler method is a discrete time version of an ODE, and the random walk is a discrete time version of Brownian motion in continuous time. So now we can start filling in this question mark over here and tell us, and I can tell you what a continuous time version of SGD could look like. And this will be called a diffusion approximation for SGD. So here are again our SGD iterations, and they are decomposed in the average gradient and this MN term, which measures the difference between the average and the sample gradient. Now, we don't necessarily look at linear regression. This, of course, many of these things work with for nonlinear problems as well. And this first negative gradient of F term is, of course, well modeled by gradient flow. But now we also want to incorporate this MN term in continuous time. So we should add a random term to our equation in some sense. And this we will call the diffusion approximation. So and one way we can do this is by looking at stochastic differential equations. So you might not be familiar with this, but basically, if we just say here sigma is equal to 0, then we have an ordinary differential equation. And now sigma is not 0. So at each time step, we sort of add a random fluctuation to our solution. And of course, there is a solution for this equation under certain conditions of for B and sigma, but without giving you a definition, one way of understanding the solution is by trying to simulate it. And one method we can use is the Euler-Maruyama method, which is just an extension of the Euler method from for ODEs. So these first two summands here are the same as in the deterministic case, but now we have a new summand here that incorporates the probabilistic nature of this equation, where we have the square root of h term, where h again is the discretization parameter, and the Zn is again our sequence of coin tosses, or something else, which is IID with expectation 0 and variance 1. And here I've run this Euler method for a small h for this SDE, where this first part called the drift coefficient is the same thing as we had in gradient flow, and then I also added a constant diffusion part to it. So this has the effect of sort of disturbing the exponential function by some random fluctuations based on this Brownian motion. And we can compare this in blue, the Euler method applied to the SDE, with this orange path for the SGD. And of course, the paths are not close to each other, but they're sort of close in spirit. And the way we can understand this is maybe by comparing the solution of the SDE with the Euler method. Here we focus on something called weak convergence of order 1. So this weak convergence means if we fix a positive time horizon and a constant c, then for all nice functions g, the expectation of g applied to the Euler method is close to the expectation of g of the solution of the SDE. And this difference goes to 0 linearly as the discretization parameter h goes to 0. So that means the distributions of the Euler method and of the solution of the SDE are close, but the individual realizations do not need to be. That means, for example, if we run a Monte Carlo method to estimate the mean by, let's say, simulating 100,000 paths for the Euler method and compare this with the mean of the SDE solution at some point, that will be close to each other, but the individual paths do not need to be. Okay. Now that we know about the Euler-Mariano method and SDEs, we can sort of we can derive the diffusion approximation for SGD. So I've written down, first of all, the SGD iterations, and then below that, the Euler method. And if we look at this, we see that we should set B equal to minus nabla of F. And by looking at the expectation, and if we look at the variance of these two iterations, we can also find a reasonable definition for this sigma. So first of all, you can see that over here we have this h, and then below we have square root of h. So we also should have another square root of h for the sigma. And then also this mn term must play a role. So if we match these coefficients, we see that, again, b is the negative gradient, and sigma is the square root of h times capital sigma, where this capital sigma is the quadratic, or is basically the variance in the gradient noise. Right, so this is now encapsulated in this diffusion coefficient. And with that, we have finally found our diffusion approximation. And we can say these SGD iterations are approximated in some sense by the solution of this family of stochastic differential equations. Okay, and in what sense? Well, in the same sense that we had before with the Euler method, we have weak convergence of order 1, right? Okay, but now what's maybe a little bit strange is that, or maybe surprising, maybe not strange, that the equation x depends on h as well. So for every learning rate h, we get a different equation and a different solution, right? Okay, so the bottom line here is now that SGD is represented in continuous time by a diffusion approximation, this xh. Now we can compare maybe the diffusion approximation with gradient flow. And of course, it's more complicated. That's a disadvantage, but let's list some advantages. We can say it's more realistic since it's actually stochastic, just like SGD. And in particular, for example, if we are close to the minimum, the OLS estimator, for example, then we generally have fluctuations around that minimum for SGD. So like non-vanishing noise. And the same thing will be true for the diffusion approximation, whereas gradient flow will just converge to the minimum and then stay there. Something else that is interesting is that now batch size actually matter. Gradient flow does not see the difference between learning with full batch, with a mini batch, or with just a single data point at each time step. Whereas for this diffusion approximation, the batch size will actually enter into the sigma term. So we can sort of study the effect of using different batch sizes. And then, of course, since it's stochastic, we can look at something like optimal stopping, where we say, okay, training has some cost associated with it, but we also want to go close to the minimum. So if you let it train, when should we stop the process in optimal sense? And that makes sense for stochastic equations. All right. Then the learning rate matters directly, even if it's constant, because it's directly in this diffusion term. For every learning rate, we get a different solution. And for example, if we run stochastic gradient descent and we choose a pretty high learning rate, so let's say h equal to 1 or even higher, then we will often observe divergence. This can never happen for gradient flow. So gradient flow will always, if it converges once or for certain learning rates, it will always converge because the learning rate doesn't even enter into the equation. Where for the diffusion approximation, we will also have divergence for large h. Although we should know that these approximations, they are bad for large learning rates, it's still interesting that both the diffusion approximation and gradient descent or stochastic gradient descent will have the same behavior. And if we do optimal learning rate control, now we actually take into account the gradient noise, so the difference between the average gradient and the sample gradient. All right. Although something that we have to consider at this point is that the gradient flow approximation is also a first order approximation, or has the same weak convergence of order 1 as the diffusion approximation. So that kind of leaves us with the question, is the diffusion approximation actually better in some sense? And we computed directly the leading error term. So this is the, here we computed the leading error term for the first order diffusion approximation. So this is this h. So first of all, we know it's O of h, but now directly we know it's h times this integral from 0 to t over this phi t of x o, which is the gradient flow, where phi is a sort of complicated function which depends on the derivatives of some function y and f. And we can do the same sort of approximation for gradient flow. So now we compare gradient flow to SGD, and we have the same result, except we now have this new term over here in the error. And importantly, this term contains sigma. So what happened here is we canceled, when we go from the diffusion approximation to gradient flow, we cancel out the sigma from the equation, but now it reappears in the error term. So that term actually is sort of important, we can see here. And we can actually visualize this. Here we have considered like many different data sets, so like thousands of data sets, and always computed these two integrals. The blue curve is for the diffusion approximation, and the orange is for gradient flow, as they are, and we computed what kind of weak error do they have with respect to stochastic gradient descent. And we can see that the diffusion approximation is actually better because the curve is actually lower. Although it should be noted that for certain choices of the coefficients, gradient flow can also be better, but on average, this is not the case. Okay. Now something else. So far, we've looked at something called the first order diffusion approximation because the convergence is of order 1. But we can actually write something down which is a second order approximation using something called a stochastic Taylor expansion. So this is like the usual Taylor expansion, but it works for stochastic processes. And using that, we can derive a second order diffusion approximation, which is the same as before, except the drift coefficient now has an extra term where we have the learning rate. And now we have the Hessian of the loss function appearing over here. And in fact, this has this weak convergence of order 2 property. So as h goes to 0, this difference goes to 0, but quadratically. So this approximation is qualitatively better than gradient flow and the first order diffusion approximation in this sense. Sorry. All right. And now for a slightly different topic. What about learning rate schedules? What about if we want to change the learning rate over time? Because this is often what we're doing when we're learning. So we have a sequence now, eta 0, eta 1, and so on, of learning rates. And we consider the stochastic gradient descent iterates with this sequence of learning rates. What we can do then is we write eta n as h times u of nh, where now h has the role of a maximal learning rate. And u is something we call a learning rate schedule. An example that occurs often, for example, is this schedule, where ut is given by 1 over 1 plus t over h, or equivalently, the sequence of learning rates is eta n is equal to h over 1 plus n. So these kind of learning rate schedules can often ensure that we actually converge and stay at a minimum, even for stochastic gradient descent. And that's why we're interested in them. And we can also incorporate these in our continuous time approximations. We have to multiply for gradient flow this negative gradient with this ut. And for the first order approximation, we also have to do the same thing for the diffusion coefficient. So this has been known before, and our error expansions for the leading error term actually still apply for this case. But another question would be, is there a second order approximation if we have a learning rate schedule? The answer is yes. And you can again find this equation using a stochastic Taylor approximation. And the difference to the second order equation I showed you before is now we have this u dot term over here. So the derivative of the learning rate schedule appears in the drift coefficient of our equation. And of course, this has not been observed before because for constant learning rates, this just vanishes. Right. So this is also possible. And we have, again, weak convergence of order 2. I think I'm very fast. Just realized that. But OK, let's get to the applications. I already hinted at some applications before, but let's look at a specific one called learning rate control. Here we have a diffusion approximation, again, for this sort of linear regression example. And for simplicity, we've chosen a constant diffusion coefficient, sigma. And we want to minimize the quadratic error at a future time point t. And we can do this using something called dynamic programming, which you may know from algorithm theory, but it also is a method for solving optimal control problems in discrete time. And it also works in continuous time via something called the Hamilton-Jacobi-Bellman equation. And with this, we can derive an optimal schedule, which is given by this function over here, which is 1 until a time point t star, and then has sort of the same behavior as the learning rate schedule we've seen before. And this is how it looks like in an example. And the interesting thing here is that we can actually get an analytical solution for this function, whereas in discrete time, this is difficult or even not possible. Another application for diffusion approximation is studying something we have not discussed before, and that is SGD without replacement. So if you are a machine learning practitioner, you might be scratching your head about our definition of SGD, because what we usually do in practice is we draw from the data set that we have without replacement until every data point has been seen once, and then we repeat the sequence. So in particular, we have a concept of epoch, which makes barely sense for the SGD method we've seen in this lecture before. So we call this process, or this method, SGDO for short. And the theory of this algorithm is rather underexplored, which is probably because we lose this independent and identically distributed property. And a natural question you might be having is, are there diffusion approximations for this algorithm? And to derive something like this, first we consider in the first epoch of this algorithm, we draw IID from the data distribution as usual. So Brownian motion would suffice as a driver for this equation. And in the following epochs, we repeat the draws in the same order. So what we proposed is using something called what we call epoch Brownian motion, which is Brownian motion first until time capital T. And then the path of this process, repeats itself after the first epoch in a continuous fashion. So here is a single realization of epoch Brownian motion with t equals 2. So you can see after time 2, the path repeats itself. And it sort of looks like this has a drift. It doesn't actually have a drift. It's just that once you know the first epoch, for example, if it goes up during the first epoch, you know it will keep going up until the end of time. Conversely, this is the same process but a different realization. If it goes up in the first, it goes down in the first epoch, it keeps doing that over and over. And we think that this is that we can, using this epoch Brownian motion, derive a useful approximation for SGDO in continuous time. Now, the diffusion coefficient somehow depends on the underlying data generating model and the additive noise in the data. But let's just take this for granted. And under this model, if we choose this learning rate schedule we've seen before, so the learning rates are eta n is equal to, actually it's h over 1 plus n, then we have convergence in distribution of this solution of this equation, where the limiting distribution has the same mean and the same variance as the ordinary least squares estimator. So in that sense, we can sort of already see that this diffusion approximation based on this epoch Brownian motion actually makes sense. And we also did some simulations. For this case here, we compared the weak error of gradient flow with this diffusion approximation I just showed you for different learning rates. And well, a curious fact about this graph is you can see as the learning rate gets close to 1, it seems, and it actually does happen, that the gradient flow suddenly becomes better. But I feel like this is not very important because all of these approximations are bad for large learning rates. And usually we don't really consider a learning rate of 1 anyway. We want to consider small learning rates. And for small learning rates, this diffusion approximation is actually better. Something else we can do is we've seen that the limiting distribution of this diffusion approximation has the same mean and variance as the OLS estimator. So we expect the same would be true for this SGDO process. And here we have actually compared the limiting distribution of the SGDO process with the OLS estimator for different sample sizes. And sample sizes also mean epoch length. And we can see these are very close to each other. So we think that our analytical derivation of this limiting distribution for the diffusion approximation actually coincides with the discrete SGDO process. And now we can even add this to our table. So we can say SGDO in discrete time is approximated by this diffusion approximation driven by epoch Brownian motion in continuous time. So here's our literature. The idea of diffusion approximations was introduced in 2015, both by Mand et al. And as well as Li Tai. And in 2018, Li Tai, after giving sort of a heuristic explanation in 2015, they developed this theory more rigorously. Then afterwards, we sort of derived these leading error expansions and also the second order diffusion approximation for learning rate schedules. And 2 days ago, we uploaded our preprint for these diffusion approximations for stochastic gradient descent without replacement. Okay, so I know I was very fast, but I hope the messages still came across. So thank you, and I'm open for questions.
Thank you very much for the nice talk.